Hi, ladies and gentlemen. I trust that you're enjoying lunch so far. And now I would like to invite you to please return to your seats and give your entire focus to the stage because we're up for an enchanting keynote session. Our keynote speech will be by Professor Reinhard Genso. While he requires no introduction, as many of you already know him, please allow me to give a short bio of Professor Genso. Professor Genso was awarded a Shaw Prize in the discipline of astronomy in the year of 2008, and amongst many other global renowned accolades, the Nobel Prize winner in physics in the year 2020 for his discovery of a supermassive compact object at the center of our galaxy. He's currently the director and scientific member of the Max Planck Institute for Extraterrestrial Physics and the chair of Board of Adjudicators of the Shaw Prize. I must say it is an utter pleasure and honor to have Professor Genso with us this afternoon. So let's give him the biggest round of applause. Welcome, Professor Genso. The stage is all yours.
Thank you. You never know if you have to speak first, whether that's a good sign. It's sort of a dubious honor. But let me try to tell you my story of a walk through a forest, a 40-year journey. Now, science and exploration is indeed a little bit like walking into a forest you don't know. So you walk in there already pretty excited what you might find. You see the trees, different sizes, different colors, and you take note of the beauty. Then you begin to notice that there are other things other than the trees, the mushrooms, flowers, all this wonderful stuff. And as a scientist, of course, at some point, you try to bring some order into this. So you have a little notebook where you write down what you found so you can publish it later on. But now, at some point, you begin to notice that there are blue flowers and red flowers. And the blue flowers, you find, are always on the left side of the path. That is a critical moment when you have to decide whether you want to become a physicist. Because a physicist means you have to understand why that is. Why is it that the blue flowers happen to be always on the left side? Of course, you want to be careful, and you may observe many such flowers, so it's not just a random little finding which turns out to be wrong afterwards. But so it is about the story I will give you today. The story is one about looking at the universe at large, observing it, of course also making theoretical analysis of it, models, and in particular the famous theory of general relativity. Now let me introduce you a little bit into that. Now we know since the times of Newton and Copernicus, Kepler, Tycho Brahe, that the sun is the dominating mass in our local universe. And we on the planets are moving about the sun on what we would call closed orbits, almost circular, elliptical orbits. Of course, you will recall that was not always known. Some of the elder ones actually had a different theory, and it took careful observation to distinguish theories. So it's not always obvious if you have an observation that you have an explanation, that this explanation is always right. So the scientific principle that any theory is worth nothing until you can prove it right or wrong. And likewise, if you have an observation, just because you say it doesn't mean it's right. There have to be others who agree with you. So we know from the work of Newton et al. That there is a force which keeps the solar system together. That's gravity. The force of gravity, which we as human beings know very well. Now I'm an old man, but the younger ones amongst you could jump high, couldn't you? But you will come down, I bridge you. You will come down, and that's gravity. And so the force of gravity forces the planets on their orbits. Now then came Albert Einstein in 1915 and presented a new theory of gravity. That theory was, in general agreement with what Newton would say, but had some additional features. One, and perhaps the most important feature, was that it took into account the empirical fact that the fastest communication we know of is the speed of light. Nothing, including light, of course, can travel faster than the speed of light. And that you have to take into account. So in Newton's world, if you put a mass somewhere, then its action would be everywhere instantaneously. No, says Einstein, it has to actually be communicated. It has to be communicated through the curvature in space-time. So his work, and then the work following, explored the mathematical ramifications of this theory. So in Einstein's world, the sun, which is that yellow ball, the big ball, deforms space-time, and planets, which like this red thing, would be on an orbit, which in this case is a path of the least distance geodesic in this curved space-time. Now comes the very interesting thing. In Newton's world, light travels always in straight lines, irrespective of whether or not there's a mass nearby. But that's not the case in Einstein's world. So in fact, here we have a picture of the sun, the Earth, and a star, which happen to be behind the sun. So in Newton's world, as the light is going by the sun on a grazing path, it would go in a straight line. Not so in Einstein's world. In Einstein's world, also light, photons, see gravity and are deflected in their path. So that means that if you now look backwards at the light of the star and try to estimate where it is, of course thinking it came along a straight line, you would not think it's where it is. You would think it's 1.7 arc seconds further up. That was one of the major predictions of the first hour of Einstein's theory in 1915. In 1919, there was a solar eclipse in the southern Atlantic, where indeed a very rich and well-known star field was covered by the sun. And Eddington and others looked at that and measured the distances of the stars as they would move behind the sun, as the sun would go in front of them. And indeed, they found exactly that deviation which Einstein had predicted. So that's a major new thing. Photons, light, which is the fastest communication we have, sees gravity. That has major connotations, because that means that if you think about the action of gravity on photons, and the gravity is strong, that can have major implications. Let me explain that in the following way. Let's look at the sun. Here's the sun. Now let's think we do an experiment by having a rocket on the surface of the sun and let it fly away from the sun. Then you can easily calculate with Newton's formulas that the speed for that rocket to escape from the sun into interstellar space is 600 kilometers per second. On the Earth, we know that from the rockets we see, is 11 kilometers per second. And that velocity is given by the mass of the sun and its size. So let's have a thought experiment and look at another sun, which has the same mass, but it is smaller. Well, then on its surface, the gravity is stronger. And if the gravity is stronger, then the speed is greater. So if we shrink the sun in our thought experiments to 3 kilometer size, then you can calculate that the escape speed is 300,000 kilometers per second. That's the speed of light. Now we make it a millimeter smaller, then the escape speed is greater than the speed of light. That cannot be. That's a black hole. So you now know what a black hole is. Very, very simple. It's an object where the concentration of mass is so large that at its so-called surface, the event horizon, the escape speed is greater than the speed of light. So you cannot communicate from within the black hole with the outside world. The other way around you can. You can also, we all can all go into one of Elon Musk's spaceships and travel to the nearest black hole. And if you're sturdy enough, well, I don't think, certainly not me, we'll move through the event horizon. We won't really notice it much. And then we will all end up in the center. There's no way to stop the rocket, says the general theory of relativity. No way to go back, no way to get out, and no way to show pictures, because we would like, of course, to report about our trip. We cannot do this. There's a complete barrier, and everything ends up in a central singularity of infinite density. Remarkable. That's a remarkable prediction of general relativity. Black holes are objects where most of its, or all of its mass is concentrated in a single point at the very center. Mathematical point, infinite density. In fact, most of us physicists think that cannot be right. There must be a change, an addition, an expansion of the theory, like it was in other fields of physics, electromagnetism, for instance, to take into account what happens on the smaller scales. We don't have that theory of, that quantum theory of gravity quite yet. But gravity is one of the most important and at the same time fundamentally poorly understood phenomena we have in physics and astronomy. Okay, now let's go on. The next question, of course, you could say, well, if there's a black hole somewhere, how do we find out about it? Obviously, I just told you there's no light. So how do you see it? Well, you see it through its action in gravity on the surrounding bodies. So if there are planets around a non-visible black hole of the mass of the sun, well, then you could measure the masses, and like in the solar system, they would obey the Kepler's laws, and you would be able to say, well, there's a central mass there, you can't see it, but it's there, one solar mass. And if you can come close enough, comparable to the event horizon, which of course in the solar system you cannot, then you would be sure it's a black hole. So that's sort of the prescription how you might think to find out about black holes. Now, general relativity was very well developed, and several solutions, including solutions of black holes, both spherical, that is non-rotating, as well as rotating, and even charged black holes, were known in the 1960s, but not much in terms of experimental verification. But then came a new observation, and that was the so-called quasars, quasi-stellar radio sources. The radio astronomers at that time were beginning to chart the heavens and were finding new sources which were not seen or not known to be very strong radio emitters, optical emitters. There's one of them, a source which is a meager little 16th magnitude star called 3C273. It's a very bright radio source, highly variable. And the radio astronomers said to their optical colleagues, why don't you check them out? Look at them with your big telescopes. And so Martin Schmidt there at Caltech used the Palomar telescope and looked at this little meager star and looked at its optical spectrum. And what did he see? He saw the series of hydrogen lines in the spectrum very clearly, but all redshifted by 16%. 16%. Wow, that's quite a bit. How could that be? Well, of course, at that time already, the astronomers had shown, Hubble and others, that the universe is expanding. And the further away something is, the faster it seems to be moving away from you. So you can use that assumption and calculate how far away this quasar is, and turns out it's 2.4 billion light years. So it had taken light 2.4 billion years. That's a significant fraction of the age of the universe. Wow. But that has a tremendous consequence, which means if you now think about the strength of the light, it's very faint where we see it. But if you extrapolate where it was emitted, of course, the dimming of the light over this large distance means that when it was emitted, there was a lot of energy. In fact, this particular quasar produces, about 1,000 times more light than the entire Milky Way with its billions of stars. And so in the 60s, many astrophysical theorists were, thinking very, very hard. How could you do that? Could you think of a star cluster or something like this? And the answer pretty clearly became no, it's not possible. And the theory which became sort of prominent over the years was a very paradoxical one: black holes. Wait a second, you say. You just told me that, light cannot escape out of a black hole. Yes, I did. Shall tell you this. But I said within the event horizon. Outside of the event horizon, light can escape. It gets redshifted. It loses energy, but it can escape. So you can turn it around. If you let matter fall into a black hole, then on its way through the event horizon, outside of it, the energy of the gravitational energy which is released into radiation can be extremely bright. It can be at the event horizon a maximum of 40% mc squared. Remember, mc squared is the maximum energy available if you have a mass m. So that's astounding. Black holes can be very powerful emitters of light, in theory. That was the theory. But okay, I told you at the beginning, you can have any theory you like, unless you have a proof for it. What good is it for? So how do we prove this? Well, not so easy, because 4 billion light years is a lot of distance. At that time, one couldn't have telescopes look at objects near a quasar and measure their motions to sort of see the Keplerian motion. That was impossible. Actually, we can do it now. We have an instrument now on the VLT which can do that, but back then that was not possible. So what do? Well, two of the theorists down there, Martin Rees and Donald Lindenbell, thought about the problem and said, well, these quasars are very rare. That probably is because in order to make them so bright, it means a lot of accretion onto these objects. And a lot of accretion is probably rare. So maybe there are many more quasars, but most of the galaxies which have a black hole accrete very little and therefore are not very bright. Well, if that's the case, you can go one step further in your speculation and say maybe all galaxies do have a black hole, including our own. And in fact, that seems to be what we now know. So jumping over, 40 years, I can say empirically we now know that almost every Milky Way, big Milky Way, has a black hole, and the mass of the black hole seems to be correlating with the mass of the host galaxy. Okay, so if the Milky Way has a black hole, then of course we have a much better chance to look whether there is this object, since the Milky Way is 30,000 times closer than such a quasar. And indeed, that is what happens, and looking at the central part of the Milky Way was sort of the next big step. So let's take a trip from the location where we are, 27,000 light years out of the center of our Milky Way into the center. Now we immediately, as you know, Milky Way is a disk galaxy. We immediately encounter a problem in the optical, which is these dark splotches there. These dark splotches are interstellar dust, which dim the light so much that in fact in the optical bands you cannot look into the center. You have to go to infrared waves or radio waves or X-rays. And so if you go in the modern world, to these longer wavelengths, then you can really penetrate this dust and look in the very center. And there you find a very, very dense star cluster, about 1 million times denser than the environment we live in our solar neighborhood. And you find a very bright radio source there, this object called Sagittarius A star, which the radio astronomers immediately found to be very compact. And surrounding that, there was gas. As you see, this pink stuff, that's ionized gas, and the green stuff is neutral gas. So when that was found in the 1970s, many people felt, well, X marks the spot, right? X marks the spot. That is, Sagittarius star might be the location where there is a black hole. Now, in Berkeley, California, there was a very famous physicist, Charles Townes, who had won the Nobel Prize for the invention of the laser, and in his later years turned into astronomy. And he knew how to build infrared detectors and spectrometers, and he basically and his students began to chart out the motions of this gas stuff. The radio astronomers used the technique of interferometry to measure the size of that radio source. And what was found is the radio source is incredibly compact. On the scale of the moon, or the distance of the moon, at that time only about 1 meter in size. We now know it's even smaller than that. And when you measure the velocities of these gas clouds, then you can, using again Kepler's laws, you can immediately show that there is a million or a few million solar mass concentration in the very center. And that you see that as you go inward on the right side there, the mass, which you plot as a function of distance from the central source, does not change much anymore. So that's a constant central mass. So by 85, I was already then in Berkeley with Townes and working. We were very convinced Galactic Center has a central black hole. We wrote a Nature paper. We were very proud, but nobody believed us. Why didn't people believe us? We had evidence. Well, the first and obvious thing is that distance we were getting to is still 1 million times the size of the event horizon. So there might be, if there's a mass concentration, things other than the black hole in there. There might be a cluster of dim stars. Neutron stars had then been discovered, and I'm sure, Vicky, you would have said, well, there's a cluster of, such objects in the very center. All of that was proposed, plus gas clouds react to forces other than gravity. There could be magnetic fields pushing the gas around and stellar winds and so forth. So back to the drawing board. Back to the drawing board meant for 40 years, ever more, ever better, ever sharper, ever more sensitive instrumentation. And, as we heard this morning, science is possible in many ways, of course, through our thinking, but also through the development of modern technology. You can ask me afterwards why I show you the Bond movie. There is a real connection here. But I mean, the fact is that with the help of these gigantic new telescopes in Chile, with the European Southern Observatory, but then also in the Northern Hemisphere with the Keck telescopes, which Andrea Guess and her colleagues at UCLA used, plus modern techniques, really very, very sensitive infrared detectors, imaging detectors, and a technique we call adaptive optics to overcome the blurring of the Earth by the Earth atmosphere of the images. We are able to, measure nowadays at resolutions, you will see that later on, which correspond to solar system scales at 27,000 light years. So it's technology which really makes all of this possible and then allows us to check out whether there's a central mass. And indeed, when you look at the first measurement series by both groups in the 1990s, we were able to see the velocities of stars, which you see there as little points in 3 different colors from 3 different years, red, blue, and green. And then the green cross in the center, that's Sagittarius star. And the motions, if you look at the arrows, are about 100 times the speed of the Earth around the sun. So you take Newton's laws, and you find a few million solar masses have to be within that green circle, and that's about a light month. So that's already less than 100,000 times the event horizon. Still not good enough, however. Still not good enough. So what do we do? Well, build a bigger telescope? Yes, we did. We combined the 4 optical telescopes of ESO to an interferometer, major breakthrough, but that was still not good enough. Nature must help. Nature must give us stars, and it did, which come very close. So close that you can actually go into the relativistic regime. There's one such star which we began to see in the early 2000s, both groups, which all of a sudden, after being sort of moving around at a 2,000 kilometers per second, made the turn around the black hole, which is the circle there and the dot, in 2002, March 2002, where it was moving at about 2.5% the speed of light. So that's unheard of. That's incredible. And so there it was clear to most people there is a real mass there. And the mass which you measure is the same. We knew all along, about 2 to 4 million solar masses, but now concentrated within 1,000 times the event horizon. So now you can exclude a large number of alternative possibilities, and most of the astronomers are quite happy. The physicists, not so. I mean, they were still saying, yeah, but you really have to be closer, and you have to actually show that general relativity applies in these kinds of environments. We all believe that general relativity is well tested. Absolutely it is. But on strength and scales, which we would call the weak limit. So how about the strong limit, near speed of light? So that was the next big challenge to overcome. In the meantime, both groups had a lot of fun. By charting out not the velocities, but actually the orbits of nowadays 100 stars coming as close as a few times the orbital radius of Uranus or Neptune, we can actually determine the mass, central mass, to about 0.1% accuracy. I mean, I grew up in a physicist's household. My father would say, yeah, astronomy, this isn't very nice, but you know nothing much better than an order of magnitude. But no, we know the mass now to about 0.2% accuracy. We know the distance to the galactic center to a similar accuracy. So this is really precision measurement techniques. And then at that precision, you're beginning to see effects of general relativity. And the first one is the so-called gravitational redshift. So if you have a star moving by a very heavy object, then of course the light has to escape that potential well. The clocks go slower there, and when the light arrives at our location, it is redshifted. And the redshift in this case is about 6 × 10⁻⁴ of the original velocity, but we can measure it. Down there you see the track where the Newtonian orbit would be a straight line, and the GR orbit is in red. And so the data clearly show that's the GR orbit. The next very powerful feature where Newtonian and Einsteinian worlds differ are the so-called precessions. If you have a star, a dominant star, and a planet, then in Newton's world, if there's only one planet and it's orbiting on a bound orbit very far away, then that orbit doesn't change. Not so in general relativity. In general relativity, there are two precessions. One is called the Schwarzschild precession. It's a prograde in-plane precession, depending on the radius from the central mass. And the second one depends on the spin of the black hole. So the Schwarzschild precession is the bigger effect. And so in the case of the galactic center, for that star I showed you, it's 12 arc minutes per orbital period of 16 years. And in 2005, we felt, if we measure well, maybe we can get that. Okay, so how well did we do? Suppose you do the same as you did on the left side. You plot in X and Y the residuals from the Newtonian orbit. That, of course, means a Newtonian orbit, now on this plot, is a dot, no change. Now, if you look at what GR predicts, it predicts all these loops. Okay, that's due to the precession, due to the Schwarzschild precession. And here are our measurements with the interferometry on the VLT. So you clearly see that we can see the Schwarzschild precession very, very well. And that has a very profound implication on how much mass other than the black hole can there be. We now know that, if you look in the vicinity of the black hole, less than 0.1% of the mass can be in a distributed mass. That's rather unexpected, because the big black hole would naturally attract stellar black holes and other objects. So we're not quite sure yet what that really, in effect means. All right, so far so good. Is it a black hole? Well, if you're a physicist, you would say, what do I have to do to make you happy, damn it? Well, you have to measure on event horizon scales. That's it. You have to go to event horizon scales. So there are no stars there, but there's gas. There's hot gas in the accretion zone, and it turns out empirically that the galactic center burps once a day. We call that flares, like the sun. Hot plasma is accelerated and then shows up as infrared radiation. And when we measure the positions of these hot blobs, they move. They move. And we are at this now for 5 years, and we have seen, certainly 10, 15 such flares. They always move in clockwise direction, and they always move on near a circle, and they always move at around 5-6 times the event horizon. And they always move with about 30% the speed of light. Well, that's a word. That's exactly what you would expect from Keplerian motion near the event horizon. Are you happy? No, you're still not happy. Well, okay, there's another technique, and that's you use the photons. I told you initially that the photons, of course, also see gravity. They're very sensitive to that. So that means that if you illuminate from the right a black hole, there it is in the center, and you look from the left, then, of course, you would think that if you're Newton, that all the rays which go past the rim of the black hole would make it to you, but the ones inside, of course, never make it to you. But I told you, GR tells you, no, the outer ones get diverted also. And in fact, within about 3 event horizons, 3 gravitational radii, the light is so far bent that it either disappears into the black hole, never reaches you. And that means that when you look at such a situation, you would expect a dark central region surrounded by a brightish ring due to the illumination. That's called a shadow. And here's what our radio astronomy colleagues have done last year. They did it before in another black hole further away, but in the galactic center, we know what the mass is. I told you that, to 0.1%. So we can predict very accurately as a prior how large the size of this ring should be. Should be 50 microarc seconds in size. And what do they measure? 51 microarc seconds. Not bad for government work. I mean, that's pretty good. So is it a black hole? Probably. Is it a rotating black hole? We don't know yet. We need still better measurement. And these better measurements will come. I'm fairly convinced of that. They will come through still sharper measurements. We are now just, as we speak, building up a 40-meter telescope near the VLT, which will be still better in accuracy. The radio astronomers are gearing up for better measurements. And we have another technique coming in, and that's gravitational waves. Because gravitational waves in an in-spiral of 2 black holes also can help you measure the basic central region. And that has already been used by LIGO to basically confirm the nature of stellar black holes. So it's a remarkable, 100 years after Einstein's work, 3 different techniques are currently being used to explore in detail, with detailed measurements, the physics of black holes. And they will continue to do so. I'm looking especially forward to a space mission called LISA by ESA, where spacecraft separated by 2.5 million kilometers will send laser beams to each other. And that's the way to really look with the greatest precision at the in-spiral of, say, stellar black holes into big black holes and really look at the physics of this. So, we've made a lot of progress. And if you look at the mass distribution in the galactic center, so to the right is far away and to the left is the event horizon, you can see that as we were getting better and better measurements over the years, we were more marching inwards with these ever better stellar measurements. And then in the last round, now with the flares and the event horizon telescope measurements, we really have a pretty good handle already on event horizon scales. And anything else is actually not much. And that's still, as I said, a riddle for the theorists to fully understand.
Thank you so much, Professor Genso. Another round of applause, ladies and gentlemen, for the spectacular and inspiring keynote speech. Professor Genso, a journey of 40 years. Amazing. I must say that science is no longer confined with scientific pursuit individuals, but laymen like myself took great pleasure in listening to his presentation. It's scientific almost to the extent it's romantic and playful towards the end with a bit of bond weaved in the middle. Thank you so much, Professor Genso. I'm sure a lot of us look forward to exchanging with you over the forum week this week. So now let's move forward to our insightful panel discussion about several science and development related topics which are concerns of each and every one scientist and those who would like to pursue science. This panel will be co-hosted by Professor Choi Lap Chi, board member of the HKLF Council and founding president of the Hong Kong Academy of Sciences, and together with Professor Kenneth Young, board member of the HKLF Council and chair of the Shaw Prize Council. Let's welcome our co-hosts, Professor Choi Lap Chi and Professor Kenneth Young, on stage. Welcome. They will be joined by 3 Shaw laureates from different disciplines, and they include Professor Stephen Bobas. Welcome on stage, Professor Bobas. Professor Gert Foutings. Professor Foutings, please. Welcome on stage. Thank you for joining us. And Professor Peter Greenberg. Welcome, Professor Greenberg. So now we have our 3 panelists on stage together with our co-hosts of the session. I would now like to pass the stage to Professor Young and Professor Choi. The stage is yours.
Good afternoon, one and all. I think we are all pleased to be here with you at this panel as part of the launch of the forum. I recall the panel discussion we had in 2019, at which quite a few of us were present. For today, we have, I think, just 40 minutes, and I think we'll just launch right into it with a question to all of you. And I'm prompted by one theme that I picked up from the lecture just now, namely 40 years on one single quest. And it struck me how nowadays scientific projects take a very long time. There is a message for policymakers, but I think for this audience, it's much more important the reflection for young people, that if a project takes 20 years, then what you start off doing now would be what you would be doing 20 years from now. So how should you choose an optimal direction, and how would you develop taste and discernment to make that choice? And how do you find the best mentors to advise you on that choice? That is a question that is on my mind. And I wonder, perhaps I could start with Professor Bauber, since this emerged from an astronomy lecture.
Well, thank you. Those are difficult questions to answer. And I don't have a magic formula for all scientists that's going to work all the time. I can tell you what my experience has been, and that is, I think it's rather difficult to try to predict in advance. It often can be very difficult to predict in advance what the hot fields are going to be. A field can appear to be very brimming with activity and ideas, and can peter out suddenly, and then you find yourself pursuing something which is not as exciting as it appeared just a brief time before. On the other hand, there can be totally unexpected observations that take everybody by surprise, and it's very, very difficult to anticipate them. Now, one of the things that you said really does ring true, and that is that you're going to be working, if the problem is important, you're going to be working on it for a very long time. So rather than concentrate on something which you think that is going to be particularly hot or topical, it's got to be something that you love doing. And I know in my own case, that is the work which I've been noted for was just something which was absolutely intrinsically interesting to me. I wanted to know, we heard a little bit about accretion disks and matter around black holes, and I wanted to know how that worked. And in particular, why did material and accretion disks, why did material and accretion disks stop being in the accretion disk and spiral into the hole? That wasn't well known. And I was fascinated by the dynamics of that problem and pursued a study of what happens to magnetized disks. And that was a problem that was of intrinsic interest to me just because of the mathematics that was presented, the difficulty of the problem. And ultimately, it's been a problem that I have been working with, at first with pencil and paper, in more recent years with sophisticated computer programs, but it's a problem that I've been working with for 30 years. And so I guess to answer your question, I've been meandering a bit. Let me try to refocus myself. The problem that you should be working on are the problems that you love, the problems that attract your interest and that you feel compelled to work on simply, for the sheer joy of it. And I think that would be the best advice that I could give.
Well, it seems to me that one could be interested in a host of problems, but some could be more important than others. And I still want to pursue this question, perhaps with Professor Faulting, especially in the domain of mathematics. Some problems are regarded as more intrinsically important. How do young people develop a feel among the various things they could be interested in to focus on things that are, in some sense, important? I think that is something that young people may not have the ability to do entirely on their own.
Hello? Yeah? Well, sort of my predecessor has basically given the advice I would give too. Well, I mean, in mathematics, it's different from other topics because sort of experiments are cheap. I mean, if you're an astronomer, you have to build a telescope, and it takes you a year, and you need funding. But for us, I mean, we just can try. If we have a new idea, we can try it out. And if it doesn't work out, we have sort of lost half a year, but it's not so expensive. And sometimes young people ask me, I mean, what our topic is, and then I say I don't know. I mean, let's say the only thing I can say is what worked for me, and it probably isn't true for everybody that it worked, and maybe I just was lucky. So I've always tried to do things which I liked and which I found interesting, and I didn't care about what other people thought about it. And so, for example, well, the main reason why I'm here is that I proved the Model conjecture, And the status where I got this was that my advisor Professor Nastold had a friend in Paris, Professor Spiro. He had new ideas. And well, I mean, it was clear that they weren't sufficient, but I found this interesting. You could mix algebra and analysis. And I think luckily for me, people in Paris didn't quite think that he was on the right path. And so I tried this, and then I just thought maybe, I won't solve it, but there may be something interesting coming out. But then unexpectedly it somehow worked out, and so this way, at the end, I got the Shaw Prize.
Thank you very much. In events such as this, we tend to bring the hot topics very often to young people, black holes, gravitational waves. So I want to put this to Professor Greenberg. When you got into, say, quantum sensing, was that a hot topic at the time?
So, no. And there are as many different ways to find out what you want to work on as there are people. And my way was that I learned about something that not only did people find uninteresting, but people didn't really believe it. The basic discovery of bacterial, the ability of bacteria to sense their own population density. And I thought that was interesting, if it was true, and it seemed worth taking a chance. Taking a chance is an important thing to do. There are a lot of points along the way that you can decide, oh, this was a bad chance, I'm going to do something else. In my case, it turned out to be true, and I had this conviction that in biology, if some creature has solved a problem in an interesting way, that will reoccur. That other creatures will have solved the same problem. And so it was 10 years before people believed it was true, and then another 10 years before people thought that it seemed important. But all the while, we were having fun, and I think that came through from Professor Balbus's, what'd you call it, meandering discussion. That if you find something that you're interested in, it's a privilege to be able to just go after it and figure out if it's true. And it's just sheer joy. So that's the way that I chose it, and that's the way that I've kept going for now nearly 50 years.
Well, maybe I pick up from the last point. Actually, I have two questions. One is encourage young people to think laterally, not to think so wildly, but then think laterally on a problem. So, and the second one is actually use of experimentation, instruments rather, right? So these science progress because of inventing new machines or instrumentation and so on. So maybe to start from you, Professor Greenberg, in your work, you're talking about bacterial sensing, that you're talking about bacteria. What's it to do with the animals or plants? Do you have any parallels that you think laterally? How are these principles that you found in bacteria could be applied to other organisms, to humans, say?
Oh, to humans. Well,
no, say something plant first. Okay.
Yeah, no, we'll go with humans. So, yeah, I mean, it's sort of interesting. I knew this question was coming, but the way that Lap Chi asked it, I'm going to answer it a little differently than I intended. So, as we learned about how bacteria coordinate their activity in response to cell density and how they produce what we call public goods only when there are enough of them together to make a difference, we started doing what I call social evolution experiments. So if everybody's cooperating to gain a group behavior, a cheater should arise that doesn't cooperate but shares in the benefit of all of the other cooperating individuals. And we can actually set up experiments in the lab and show that's exactly what happens, and we can measure the benefit to the cheaters in the population. And when I'm describing this work in seminars, I use the analogy of tax cheaters in the United States. So what we're finding does apply to the human condition, and we can model this and understand how much of a cost we can make cooperation incur before cheaters run rampant. And this is actually, economists were onto this before I was, but there's a convergence of fields now, sort of social economics and socio-microbiology, if you can believe that, Lapchi.
Right, no wonder you describe your interest having interest in social behavior of bacteria, so they actually extend some of the principles to other organisms, animals, and so on. So I think the other two are thinking about this. Any of you want to comment on that from your field? How can you generate things from, or to extend it to another area? Okay, all right.
In fact, it's an interesting, I mean, I have to think about it, but it's interesting that you brought that up. That actually happens fairly often in the sort of kind of theory work that I'm engaged with. Chance favors the prepared mind to some extent. And in the work which I got the Shaw Prize for, which was to look at the effects of turns out, very weak magnetic fields and accretion disks can have profound effects. I was influenced in my sort of judgment to pursue that problem because I saw something like that happen very similarly in a very different problem in astronomy, whereby I was looking at how gas cools in great clusters of galaxies where you have X-ray emitting gas at very high temperatures, and there are all kinds of interesting issues that are associated with that. But it turns out if you look at that problem in detail, the effects of magnetic fields can be very subtle, and even a very weak magnetic field can have a profound effect in terms of how that gas evolves. And when I worked on that problem at that point, I don't think there was another human being, let alone astronomer, on the face of the earth who cared about it. But I was kind of a nerd, and I was just completely taken with the idea. And so I was an audience of one for a while, until it turns out that that very same type of effect manifested itself in a system where a lot of people cared about what happens.
Wonderful.
So yes, that's a very important part of scientific research, the fact that there are these sort of commonality of ideas.
Thank you. Professor Faltings, do you have any analogies or parallels?
Well, I mean, it's sometimes possible to use techniques which from one end on the other but I wouldn't say it's a rule. I mean, sometimes you can look somewhere else and then you find something which is useful, but I think most of the time you have to think yourself.
Great. No, I always encourage the students to listen to other people, talk about other problems. Sometimes insight, an idea may arrive and unexpectedly. So it's coming about ideas, and then I talk about instrumentation. So comparing ideas and the instrumentation, improvement of technology, which one is more important? Having ideas first or having some instruments first? What's the interplay? Okay, two experimentalists first. Okay.
I'll go on that. They go hand in hand. Absolutely. I don't develop instruments, but I have benefited from the work of people who do. It's just as important. I know what I'm good at, and it's not developing instruments. I'm good at using them. Oh, here's a new instrument. I have an idea about how to apply it.
You tell them what to do for you?
No, they always say, here it is, and here's the instructions.
For the developers, perhaps you work the other way around.
No, I'm a bit like that myself. I'm a consumer. I'm not really a producer of instrumentation. I think you got a very good idea from Professor Gensel's talk this morning of the importance of, astronomy and astrophysics is a very data-driven field, and the progress, certainly over my career, has just been absolutely stunning. And certainly the work that I have done, I would agree, they absolutely go hand in hand. Technical developments on the instrumentation side, or they spur people to think of problems that they wouldn't have thought about before. I guess most recently has been the astounding success of the detection of gravitational waves with these incredible interferometers, and I still can't quite get my head around it when I describe how you can measure motions in space which are 1% of the proton radius and have a very clean signal. If I were looking at a review, I would throw it out of hand, without a second thought. But this is the sort of thing, that's a large signal by today's standards. But anyway, the development of those kinds of instruments have now had a profound effect on astronomy, because it's revealed the fact that there are probably stellar populations that give rise to these merging black holes that we don't understand fully. And so there we've gone from a very technical development and instrumentation to something which is having a much more profound theoretical impact in how we think about stars.
What I hope that you would say was that you actually tell the instrument developers to develop something for your work. But anyway, so let me move on to Professor Faltings. In mathematics, of course, do you use computers, AI, to help you solve problems?
I must say, don't use computers. I'm not very good at it. I've used it, and when I've done some computation, it turned out that it gave a totally wrong picture. But I know that computers have become important in mathematics. One reason is that sort of algorithms are now important. So in the old times, there were problems which you couldn't compute anyway, so you didn't worry about this. But now there is a possibility to use a computer and to do something, and then you have to think about the best way to do it. And it's sort of ironic also in the early 1900s, there were discussions about set theory, because there were some paradoxes, And there were some people who sort of said, I mean, you cannot just say that something exists, you have to find a way to construct it. I mean, for example, you could say the square root of 2 is a number between the numbers whose square root is less than 2 and whose square root is more than 2. But then in the theory, you have to find an algorithm to do it. And this sometimes, in that theory, it sort of died because, there were no more problems like the paradoxes, and so people got used to just work with it. But then this sort of is now coming back because there's an emphasis on algorithms. So I think the computer science has some influence. Artificial intelligence, I think, so far hasn't come. I mean, the only thing is there are people thinking about checking proofs with the computer, and there's some progress.
Yeah, I don't want to occupy the stage yet. Kenneth?
No, if I may pick up on that point a bit further, if I define instrumentation a bit more broadly for mathematicians, not just computers, but using the techniques and theorems proven by others recently as a set of tools that help you in your own work, theorems, results in slightly different fields. Call that instrumentation in the broader sense. Is that important in the work of a mathematician? And to keep yourself knowledgeable about what's happening in neighboring fields?
Of course, you always import. I mean, you depend on other people, and you have to find out what kind of ideas they had, and then you try to steal it from them and use it yourself. But I mean, in general, sometimes also there are mistakes. So you usually can't just say, I'll quote the theorem from there, and then it's okay. Usually, I mean, it's better if you try to understand how we got there.
Thank you. If I may take off from there, from instrumentations to the need for techniques, experimental or mathematical techniques that you have to spend time learning and developing. I mean, I see it as almost a tension, a dialectical tension between having interests in a very broad sense, which tends to engage young people, and spending quite a lot of time and effort learning could you call it Tao stuff? Experimentally, learning how to pipette things, how to dissect things, how to put up improved instruments. There's a lot of technical stuff that especially young people have to get through. And that is, to me, a bit of a tension between that and the broad ideas. And nowadays one sees that many young people do not spend, in my view, enough time learning the basic technology, the grunge. So how would you see this tension, these two sides to this coin?
Well, in some sense, I mean, the young people can usually learn the latest technology, and we old guys, we have at our technology, and we don't like to do new things. I mean, it's like the IBM, they built good mainframes, and they also constructed a good personal computer, but because it would cut into their business, they didn't sort of pursue it. And I think it's similar. I mean, well, I'm getting old, and I sort of find, I mean, that maybe I know too many things, and then it's difficult for me to do new things. But I mean, when I was young, for example, in my field, I learned from Grothendieck, and then usually, I mean, the older guys didn't like this. They said, we don't need this anymore, but I learned this and I profited. But of course, for the young people, they cannot spend their whole life on just learning. They also have to do something. And I mean, doing something is different from learning. So usually mathematicians have their best time between 30 and 40. Before that, they have to learn, I mean, not only the technique, but also how to do research. And over 40, maybe they get senile or something.
Thank you. But I do see a tendency nowadays, I think that's probably true for many of the young people present here, that they go into research quite early. Sometimes we see sophomores saying they are doing research before really learning what we call the basic stuff. I noticed in the promotional video for this conference, the video showing Professor Balbus, I noticed on your bookshelf a number of familiar books, Jackson, Mr. Thorne and Wheeler. But young people nowadays don't spend time plowing through that stuff. So how would you strike the balance? How would you advise young people to navigate this challenge?
Well, that's an interesting and probably a somewhat controversial question in astronomy, because it's a field which, well, I'm stunned when I talk to young people and find that they don't own textbooks, that courses that they take don't use textbooks. It's based on professors' notes. And to me, it would be inconceivable that you could master a subject without learning from the masters who wrote, the famous textbooks. Astronomy now has become sufficiently technical with its absolutely massive data sets that require processing and statistical techniques which are extremely complicated and very demanding of one's efforts to master and to utilize. And there is what I view as sort of disturbing tendency in the field for people to think that astronomy and astrophysics is itself techniques of manipulating large data sets. It's a tool, it's not the discipline itself. And I'm not sure exactly how, to strike the balance, except that in the graduate programs, that I'm involved with, that's a point that I like to stress, that there is a difference between the techniques and the science, and of course you need both to make progress, but the techniques in and of themselves are different from the science.
Perhaps that's about the systematic learning or teaching, is that?
Well, yes. There's, I think that's very important, and the potential difficulty is that, as you say, people are being pushed into research at kind of an early stage, often in their undergraduate careers, which I think is a bit too early, and that tendency, I think, aggravates the problem by stressing techniques over mastery of the ideas. For a field to make progress, people have to understand the fundamental ideas and the fundamental science, which are the foundations of it.
Yeah, I'd just like to comment a minute. I think biology is a little bit different, where you can get some experience in the laboratory or in the field and at the same time continue your didactic education. And this was really important to me because when I went to college, I thought I wanted to be a marine ecologist. And I got experience doing that, with the gumboots on and going out in the rain and the cold and counting things in the intertidal zone. I didn't really find that super interesting. But I also got experience in a laboratory between my junior and senior year, working in a laboratory, doing experiments, and feeling the culture of the laboratory. And I knew I had found my home, and then I was going to do whatever it took in my formal learning to be able to have a career doing that. So I think your field is different. I mean, it's such big science, and there are huge teams, and the laboratory, the biology laboratory, is a much smaller enterprise.
Right. I think to me, there's a big difference between biology and the other mathematics and astronomy for the present discussion. I think for the physical sciences, I think, including mathematics, you really need a systematic learning, step by step. You have to do this one before you learn the next one, and so on. But biology is somewhat different. Okay, you learn all the phenomenon first, and then you don't get the basics. And then if I had a chance to change the syllabus, I would teach DNA and genetics first, but this is a separate topic. Let's get to the conversation here. Okay, so what happened is that the people, actually I picked up from Professor Balbus, talking about asking the undergraduates or even high school students, now primary students, to do experiments, to do the so-called invention, and to do some innovation. I'd like to hear from the laureates.
Well, I think it has to be done, with some degree of forethought. I wouldn't say here that you should spend your time as an undergraduate doing nothing but taking courses and wait until you're a graduate student before you have your first exposure, to working in the laboratory or working with data. But it's not a way to start. I think you have to have some kind of a foundation in the basic ideas. And the basic ideas are complicated, and they demand effort, and they demand time. But to have observations and techniques which are sort of untethered from some kind of a coherent scientific structure in which they exist is, I think, not a very helpful way forward for a young student. They should be understanding the context, and they should learn the difference between techniques and science at an early stage.
Thank you. No, I'm actually drifting from one topic to another, because how about you, P?
So I'm trying to remember the question now. Can we bring it?
Undergraduates or primary students to go to a laboratory and do experiments?
Yeah, so I agree with Steve. You have to do this carefully, but I think it's important to show even primary students the scientific method. You can present some biological conundrum to them. I mean, I've done this with algae that make light, and they only make light when they have oxygen and when they're agitated. And you can bring the algae to the primary students and ask them to start making observations, and then ask them to come up with hypotheses, and then ask them how they can test those hypotheses and sort it out. It doesn't replace sort of the formal knowledge you have to get, but it shows them at an early age that there's a process, and some students will really take to that. And I think that kind of thing is worth it at a very young age.
Mr. Faltings, do you have any ideas about this topic? A little bit tough for you.
Philosophic. Well, I don't know. I mean, well, it has been said before. I mean, you should do the things which you like, and you shouldn't look what other people think about it. And I mean, I also can give the advice. I mean, for example, in mathematics, the most famous problem is the Riemann hypothesis, and it doesn't make sense to ask the old guys how to solve it, because if they knew, they would have done it themselves. And I always, I compare science, doing science to, for example, if you look for a parking space, if you follow the guy before you, and even if he takes always the most promising turns, if you follow him, you will only get the second space. And sometimes it's good to take another turn and then to try. Either you have bad luck or you have good luck.
Okay. Me again? Well, I have a stock question. I always ask scientists this question. How do you teach students innovation?
Oh, I can't teach them innovation because, if I knew what to do, I would do it myself. I can only, I can teach them the technique, and then even how to do research, you have to learn, As I said, it took me some time to sort of really do something new. And for me it was helpful to look at sort of ordinary people who weren't famous and they could make a living out of doing mathematics. And so I thought I can do this too. But it may be different for other people. But I cannot... I don't know how to make out of a good student a good researcher.
Okay, quick answers from the other two.
It's very difficult to actually sit and teach innovation. One of the statements, my favorite quotes from the physicist Dirac, was that he never did anything important that didn't start by playing. Rather than sort of sit and actively sort of teach innovation, I think what's important is to work closely with students at a blackboard to talk about problems which are only kind of half-baked as you approach them, and kind of lead by example and impress upon them that you don't have to approach the problem in a very deeply systematic way. Nobody does that with a very difficult and important problem. They're always messing around at the beginning. And I think to show by example how that can sometimes work out and sometimes not work out is probably the best way to encourage that kind of attitude.
Okay.
Yeah, just quickly. So following on both of your comments, I don't teach innovation, I encourage innovation. And I encourage risk-taking. And if someone working with me takes a risk and it is a complete flop, I applaud them.
90% of the time, that's what will happen. And so there's a certain tolerance that you have to get used to when you do science, that almost all the time, if you have a eureka moment, it's a false eureka moment, right? And persistence is the key, and at some point, things will fall into place.
Right. As I always say, that the scientists, at the end of your study, you get a doctor of philosophy. We become very philosophical towards the end. Anyway, Kenneth, you want to wrap up the session? No, I think it's been great because we have exceeded a lot of time. And then I see your clock, you see mine is 00, but yours is like over for 2 minutes already. Yes, I just give back to the MC.
Thank you very much. Thank you. to our professors and our two co-hosts. That was a thought-provoking session. Thank you very much. Please do be seated. Thank you.